let's go to this. So good morning, good day, good afternoon. So if the class falls in the afternoon, of course. So we will have our heat and temperature discussion. This is an introduction to calorimetry, and they will probably be a knowledge that you will need when you go into your thermodynamics. And thermodynamics is about heat that eventually flows. So it's an important knowledge in the field of engineering. So thermodynamics is one of the lessons that is covered, especially if you go into mechanical engineering. But there's a basic uh, thermodynamics that is taken up by all engineering students. So um, the same is true with electricity, with civil engineering of basic lessons. So in your first year or probably second year, you will encounter the basic subjects that all engineering students will eventually take up. That is if you proceed to engineering, of course. So thermodynamics will mention about heat and temperature. So let's discuss this zeroth law of thermodynamics. If a system is in thermodynamic equilibrium now with system B, and likewise, a system B, is in thermodynamic equilibrium also with system C, then A and C are in thermodynamic equilibrium with each other. So, for example, we combine together systems A and B, and somehow A is quite separate from C, in some case. So it's just like the principle in math. If A is equals to B and B is equals to C, then we can therefore conclude that A and C will probably in the same state, and they are in an equilibrium state. So that's the zeroth law of thermodynamics. Now, some effects of heat, guys, when heat is introduced to a material, materials will either expand or they will contract. So a metal, for example, if you put the metal in the fire, you will notice that that metal will eventually elongate or it will expand in all directions. So a metal rod, for instance, will eventually become a little bit longer. Now, that elongation will not be very, very obvious, but if there's a device that's going to check it out, actually there is really an elongation. When I say elongation, it will become a little bit longer. So if it's 1 meter long at the very beginning, when you heat it up, it will become more than 1 meter long. So that's what happens when energy, like heat, is transferred, or absorbed by a certain material. So molecules of a substance that is exposed to a higher temperature move faster, due to the increase in kinetic energy of the molecules. The resulting movement changes the average distance separating the molecules of the substance. Thus, expansion takes place. So we are talking about the molecules there, or the atomic particles, that when they start to vibrate because of the added energy, due to heat, then they tend to move, relative to each other, they will move much further from each other. Now we always experience this in the most obviously in the case of a solid, and in metals, basically. So an expansion of a substance depends on the material from which it is made. So some materials will expand when you cool it down, when you put it at a very low temperature. So it will have an opposite effect probably, in most instances. Now I will say that in most instances, because there's a vast difference when you deal with water. When water is involved, guys, if you make the temperature of water go lower and lower, and it will reach up to a temperature of around 4 degrees Celsius. So from a high temperature, you let it cool down until it reach 4 degrees Celsius. The nature of water is that the water will start to shrink. It will become smaller. However, if you continue cooling it down, if you continue the process of cooling down water, no? So from 4 degrees Celsius, if you make the temperature even more lower, no? Go lower, no? Like you reach the freezing point, no? From 4, you go lower to 0 degrees Celsius, and you could go even negative degrees, no? Celsius. Now, the nature of water, water is an anomalous material, as they call it. Water will now begin to expand, no? As you make the temperature of water gets less than 4 degrees Celsius, the nature of water is that it begins to expand. That is why now your parents or your mother, will always tell you that you will not put, water in a bottle, in a glass bottle, and freeze it in the refrigerator. No? Why? Because when water freezes, the glass bottle will eventually break. No? Why did the glass bottle break? Because water eventually expands, after it reaches a temperature lower than 4 degrees Celsius. Since freezing point is below 4 degrees Celsius, then water will now start to expand. And you'll notice that the container it is holding, the container that holds that water will eventually, break apart if it's brittle, like glass, and other breakable materials. So we always put water in what types of material? In plastics, so that it will not break. So with the exception of water, since water will expand, at lower temperatures, other materials will shrink. Like for example, if you have a ring, and you let another metal go through a ring, but eventually, at the very beginning, uh, um, the two materials, will not pass, they will not pass through each other, now what do they do so that the other material will enter, the ring? They will heat it up, they will heat up the ring, and probably they will cool down, a metal ball. And at the very beginning, the metal ball cannot pass through, the ring. But when you cool down the metal ball and heat up the ring, you'll notice that it will now be possible for you to shoot or let the metal ball, pass through the ring, because the ring will expand and the metal ball at the same time will shrink. Again, the nature of thermal expansion. Um, do you have a question about that? Now, different
Sir.
materials expand, by different amounts, So they don't expand, different metals expand at different rates, So if you have a copper and you have an aluminum, if you heat them up, side by side, you'll notice that one of them will become longer than the other, The other material will probably, expand, less ang iyang pag-elongate, Now, we observe that in a bimetallic strip. A bimetallic strip is made up of two different sets of metals. A brass. A brass, again, is an alloy. It's a mixture, I guess, of copper and bronze when you mix it up. Now, steel is a mixture of some kind of iron and other metals. So both brass and steel are alloys. So alloys are simply mixed. They are a mixture of two metals together, at different ratios. Now, if you put side by side the brass and the steel, you can now call it as a bimetallic strip. There are two metals. Bi means two. So if you put them side by side and you heat it up, you'll notice that at the very beginning they may be straight, but you'll notice that when you heat it up, if brass expands faster than steel, you'll notice that eventually it will now bend. There's a possibility for the metal to bend because one material, is expanding faster and the other material cannot cope up, so therefore it will have a tendency to bend. Now, once it bends, bimetallic strips are used as a kind of a switch. You'll probably notice that in your flat iron, while you iron your clothes. You'll notice that at certain temperatures, if you set the knob, of of the flat iron, you'll notice that it will switch off, no, automatically. No? So you will wonder what causes it to switch off. Now again, because of that bimetallic strip, no, that at higher temperatures, when two metals are put side by side and it will bend, no, it can act like a turning off of a switch. No? But it is doing it, no, in no, in an automatic way and with the use of a certain temperature. No? So at a certain temperature, a metal will expand at that value specifically, and therefore, no, if it's bending and straightened, no, from time to time, and then it can act like a automatic switch. No? So again, no, brass expands more than steel, no, when heated. No? So when a bimetallic strip is placed on flame, it curls, no, toward the steel part, no, of the strip. No? Can you imagine that? So again, no, side by side, when one material, no, if they are placed, no, or bonded together, it will curl, no, it will bend, no, when it is heated, or it will go back to its original shape when it is cooled. So the nature of thermal expansion. No? So again, no, some applications probably of that bimetallic strip is used as a switch. No? Now, materials will not only expand on its length, no? We call it linear expansion, but it can also expand, no, in all sorts of directions. So literally, it can expand, no, on its area. And if it's a three-dimensional object like a box, if it expands in all directions, then we can notice that it will have a volume expansion. No? So the volume of water, no, before you heat it up is different to its volume when you boil it. No? So the reason why water spills out of your kettle, no? So if you boil water, no? So at the very beginning, you'll notice that the water, no, can be contained, no, in a certain um, kettle or bowl, no, or maybe, no, you place it in a casserole, no, in your kitchen. But when you put flame underneath the water in the casserole, you'll notice that water will now start to get higher and higher, no, because it is expanding, and then eventually some of it will now spill out. No? So the spillage there is a proof that water do expand, no, in its volume. No? So the volume of its container cannot hold the expanding water, therefore there's a spillage. No? So again, no, the effect of an added heat or an increase in the temperature of a material. So there's linear expansion for length, no? And no, you could have a volume expansion if it's a container. No? So we deal with some value called a coefficient of expansion. No? There's a thing we call as a coefficient of expansion. No? So again, if you have a flat object, no? Like a flat bar, a metal sheet, no? So the metal will not only expand on its length, but also on its width. No? So therefore, you'll notice that a roof, no, if you have a roof, our roof is usually made of metal sheets. No? So on warmer days, no, like noontime, you'll notice that some of the parts on our roof are squeaking. No? Why do you notice that it is producing some kind of a sound? No? So if you happen to sit by, no, if you can recall, no, sitting on the covered walk, no, of CPU, no, beside the UI building. So during noontime, no, if you notice that those areas that is, no, subjected to underneath the heat of the sun, somehow, no, they sound, no, they produce some kind of a sound, no, if you are underneath there, no. And if you put science into it, then probably, no, it can be explained that that sound is simply, no, the expansion of the metals, no, that or the roof of the covered walk, no. So as they expand, no, then you'll notice that they have some kind of a sound that they are producing. So here now is a proof that the metals expand in all sorts of direction. No? So if this is a hole, no, in our metal sheet, then this hole will become a little bit larger when it is subjected to higher temperature. And therefore, when you also cool this down, it has a possibility that this one will shrink, no, or will become a little bit more smaller. No? So we call that as thermal expansion. No? So again, now we will have probably, no, for expansion, uh, when we cool down, no, the exception there is water, and we call water as a substance that is an anomalous substance because it has a different ability, you know, that when it is cooled lower than 4 degrees Celsius, it tends to expand already. Now because of that nature of water, is water is that property of water good or bad? That water expands when it's cooled down. Now, some good effects when the water do expand, no, when cooled down, is that it floats. No, the cooled version of water or the solid version of water is called as ice. No? An ice, you'll notice that it is always floating in water, no, because its density becomes lesser. No? Now, given the same mass of liquid water and the same mass of an ice, but the volume of the ice is larger than that equal amount, no, of water, you'll notice that their density now are different. Again, if you recall, density is mass divided by volume. So if one material is larger than the other, then therefore, no, its density is different. Now, the one with a larger volume, no, for the same amount of mass will have lesser density. And materials that have lesser density will tend to float on a material with a higher density. No? So liquid water has a higher density than frozen water or ice. So therefore, ice floats in water. No? Now, because of that, no, because of the expansion of water when it reaches the freezing point, that it floats in water, and then therefore, no, it seals the top of the water during winter time, no, since they are floating. No, so ice, you'll see people, no, skating in the frozen lake, no, because the top of the lake is now, no, solid ice. Now, that is one good effect of water, that water freezes, no, and floats, so that, no, below that frozen portion of the water, it is still liquid and aquatic life can still survive. So fishes, no, and other aquatic life like some plants there, no, algae, no, they can still survive even in winter time, no, because it will seal off, now the top with an ice. However, no, not all the water in the lake is frozen. No? Now, if that's not the case, that water will not float when frozen, then probably, no, the entire lake would have been frozen, no? And that will not be good, no, for aquatic life. So again, no, some strange things about the nature of water, which is an exception to our thermal expansion. No? Do you follow? I hope you do. No?
Sir.
I will upload this video, by the way, no, and share it with you. So heat and heat capacity. No? So different substances have different heat amount of heat that it can absorb. No, now which one, no, can hold more heat? No? Uh, Usually, no, heat is a matter of the mass, no, of the object. No, like for example, if you have a glass of water and, no, a huge uh, casserole, no, a casserole full of water, no, and you heat them both, no, you'll notice that the amount of heat of the two different masses of water, no? Like one is again, no, in a glass, no? Like you boil water, you put it in your cup, no? You'll notice that the amount of heat in that cup is not the same, no, with the amount of heat that is placed in a huge container, no? So bigger masses, no, tend to hold more heat compared to a small glass of water, no? Now just imagine, no, if that boiling water in a cup, no, spills over your arm, no, naula siya, bisay mo kamot, no? Pero that's a boiling water, but the boiling water is in a cup, no? Now you'll notice that you'll get burned, no, mapasok agad na, no? However, it will not be the same kind of burn, no? Hindi na parehas mo paso, no? Kung isa lang ka baso nga tubig kaysa sa isa gid ka kaldero, no, nga tubig ang naula sa kamot mo, no? So you'll notice that the burn probably will be much more worse if that entire, no, casserole, no, the boiling water there maula sa imong yung body part, no? Probably you will have a serious condition kung mo na, no? Pero siguro that one small cup could make you burn, no? But it will not be that worse, no? Maybe you can just have a home remedy for it. But if you will have, no, a spilled water in your arm, na dako in your container, probably you'll go into the hospital and you'll stay there for quite a very long time, no, to recover from that burn. No? So burns are in degrees. No? Mayroon na nga third degree burn that is really, really serious. No? So heat, no, in heat capacity. No? So the amount of heat that we can put in a material maybe, no, defined as its heat capacity. No? So different substances have different molecular configurations. No? The cohesive forces that hold them together are also different. No? Thus, when equal amounts of heat are added to equal masses of different substances, the changes in their temperatures may also be different. No? For example, a crust of apple pie straight from the oven, no, may be eaten comfortably. No? So it's a very hot apple pie. No? You can, even though it came out of the oven, no, you can still put it in your mouth. No? But maybe, no, there would be some kind of a heat. No? But no, but it's filling. No? So those things that are in the apple pie, no, probably you could not eat it up. No? So the crust, the outside portion, you may probably, no, get a bite of it. But once you enter into the filling, no, the one that is inside, then you'll notice that, no, your tongue, no, could not contain the heat anymore. No? Okay, so like eating the Jollibee product, no, ina balang that's called as an apple pie also something. No? Now, when you try to bite the outside part when it's crunchy, no, uh, do okay pa, no? But by the time, no, ang peach mango pie na bala nila, no, after they serve it to you, you'll taste sa imong nga dila na ang iya nga crust nga crunchy. You'll really like it, but by the time you enter into that feeling, no, that is so hot, no, then you tend to blow your mouth, no, mahuyok-huyok kuna na sa baba mo kay napaso na dila mo, no, so something like that, no. So different materials there provides, no, different amounts of heat, and we call that as heat capacity, no. So heat is an energy, no? So we can always call it heat by the time na nag-flow na siya, no? So usually the heat flows from a body of lower temperature or a body of higher temperature, and it will transfer to a body of lower temperature, no? So if you put side by side two different, no, materials of different temperatures, then they will tend to, no, cause energy to move out, no? Initially, the body has what we call internal energy, no? So body A and body letter B, no? They have different temperatures. So we call the energy of the body there as internal energy. But when you put them side by side and they are now in contact, you'll notice that the internal energy will now go out. Huh? So we call that energy that goes out from a body of higher temperature to a body of lower temperature as heat. No? So that's the time when it goes out. No? So heat flows from a hotter body to a colder body. no, and not the other way around, no. When two objects are placed, no, in thermal contact with one another, no. Now there are so many ways of transfer of heat, no. There's conduction, there's convection, there's radiation, no. These are many forms of how heat is being transferred from one material to the other, no. Now the temperature of boiling water is higher than the normal body temperature, so we feel hot, no, when we touch a pot of water, no. So again, no, init siya nga botilya, ginuyatan mo. So what happens? The temperature transfers to your body, no. Now, when you have a fever, now why do you chill? No, nagakurog-kurog ka. Why do you chill? No, why is it your body shaking? No, when you have a higher temperature, like you have a fever, no. Now, when you have a fever, we try to bring down the temperature to your normal body temperature of 37, no? I think that's 37.5 degrees Celsius. Now, why do we have to lower down the temperature? It's because when we have a fever, our body heat is going out of our body, no? Since it's going out of our body, then we feel cold, no? That's why we chill, no? So as much as we can, we have to make our body, no, reach homeostasis again, no? That normal temperature, no. So that's why mainom pagid bulong, no. You have to address the problem of the fever, no. Otherwise you will lose body heat, no, and that's not good, no? So again, no, we feel cold again because of the losing of heat in our body, no? So that's what happens when we chill during a fever, no. And temperature, no, on the other hand, no, when we touch the glass of ice, we feel cold because our body, no, temperature is higher than the temperature of the ice cold water. So heat from our hand, no, flows to the cold water. So manang matugnawan kita, no. We put our hand in a bucket full of water, no, with ice. Pag butang mo sa imo kamot sa bucket with ice, you'll notice that you'll feel cold, no, because again you lose heat, no, to the cold water, no. Now usually our hand, our feet, our head, no, this is our thermostat, no. Try to blow or to put, no, cold water on your feet. You'll notice that you'll now get colder, no. Medyo tugnawon ka na, no. You expose your hand, no, to cold temperature, you'll also feel cold, no, because these parts of our body are what we call, no, thermostats, no. So dira tana matugnawan, no. So we always cover our head, we cover our feet with socks, no, during cold time, no. And tistingi bala nga habuli lang ti mo kagang kamot mo, you will not feel cold anymore, no. So again, no, these are uh body thermostats nato, no. So the head, no, tugnawan mo ulo siponon kana dayon, no. So we have less than a minute and we will be cut, no. Kindly click the link again when we get cut, no.